standard pressure, we call it a lot of different things. We can call it 1 atmosphere. We can call it 101.3 kilopascal. We can call it 760 millimeters of mercury. But we can also call it 15 pounds per square inch. Actually, I think it's 14.9 pounds per square inch. And that means the air pushes down 15 pounds for every square inch. So that'd be like taking this 15 pounds and, you know, put your pinky under there and ow, that doesn't feel very good. But this kind of weight is touching every square inch of your body. As you can see, I have a piece of paper and I put a paint stirrer, piece of wood, underneath the paper. Now what we're saying is that every square inch of this paper has atmospheric pressure pushing on it. So that's quite a bit of pressure going down on this piece of paper. Let me show you how it works. Okay, I'm going to hit this stick. Now we know that if I hit it in a certain way, everything will just come flying, right? Well, take a look. I bet you didn't expect that. You can see that the pressure of the paper held that stick down so I could break off the end without the paper moving significantly. Another demonstration of pressure is using a manometer. Actually, this is the basic component in barometers. All right, I'm going to add some water to it. All right, you can see that in this manometer, on both sides, we have the water, and notice both ends are open. So what we call it is the atmospheric pressure is allowed to go into the manometer. So both sides have atmospheric or air pressure going in. All right, now I'm going to do something a little different. You'll notice that the pressure on both sides is the same. How do you know? Because the manometer level on both sides is the same. So that means the pressure on the left and the right from the atmospheric pressure is the same. All right, but let's change it. Okay, you can see now that there's a difference. This side, the right side with the stopper, is higher than the left side which is open. So we're going to call it this way. We have the atmospheric pressure in the open end, that's going in, and then we have the gas pressure is inside the manometer now between the stopper and the water. So that gas pressure versus the atmospheric pressure, which one is greater? And how do you know? So if you look at this, you notice that the air pressure side, the atmospheric pressure side, is pushing down more than the gas pressure side. That means the atmospheric pressure is actually greater than the gas pressure inside. So let's just make up some numbers. Let's say that 760 millimeters of mercury, which would be standard pressure. All right? And we could actually calculate this out, but I'm not going to do it because we'd have to do a conversion for water, which is 13.8 times less dense than mercury. So we're not going to do that. We're just going to make it up. It's obviously less for the gas. So let's say it might be like 755 millimeters of mercury for the gas pressure inside the manometer. Okay? Now let's switch it around again. Okay, if you look at the manometer, now you see the atmospheric pressure side is much higher than the gas pressure side in between the stopper and the water. And again, let's just use 760 millimeters of mercury standard pressure for the atmospheric pressure. Now you can see that the gas pressure is greater because it's pushing down more. It's like having a pushing contest against a friend. Whoever pushes harder is going to move the other one. So here the gas pressure is pushing down the water and pushing it up on the atmospheric pressure side. Now again, this is water, so if we wanted to do true millimeters of mercury, we'd have to do a conversion factor. We'd measure the difference in height between these two sides and then divide it by 13.8, which is the conversion factor of density between water and millimeters of mercury. But if this is 760 atmospheric, then the gas pressure here is probably like 770. It's millimeters of mercury. It's greater than the atmospheric pressure side. I'm going to show you a relationship between pressure and boiling. And here's just a syringe. It's 60 milliliters. I'm going to close it up here, and I warmed up some water. I'm going to suck the water up into the syringe. And then make sure that, okay, I want to get those air. I want to get that air bubble out of there. There we go. All right. Now we know that boiling literally is just producing bubbles in the water. So I want you to watch what happens as I pull back on the syringe. See it? It's boiling. Isn't that cool? Still boiling. I decreased the pressure by pulling back on the syringe, and it caused the water to boil. Okay, now I'm going to let it cool down a little bit more. We've actually done this with a thermometer, and we've gotten water to boil at 55 degrees. Okay, still boiling. See the bubbles? Not vigorous or anything. Oh, there's a good one. Pull it back, decreases the pressure, and it causes it to boil.